Have you ever really thought about the limits of our computers? I don't just mean speed or memory. I mean a hard, physical wall built out of energy. We have built some truly incredible things with silicon, for sure. But to make that next giant leap, especially in AI, we might just have to leave silicon behind. Today, we're going to explore how AI is turning to a brand new and yet much, much older processor, life itself. So here's the core of the problem. According to researchers, if you wanted to build a computer out of silicon that works with the same power and incredible efficiency as a human brain, you'd need 10 megawatts of power. That's enough electricity to run a small town. All of that, just to do what's happening inside your head right this second. It's this massive energy barrier that's becoming a huge roadblock for the future of AI. And this slide really puts it all into perspective. On one side, you've got our digital processors. They're getting insanely power hungry as AI models get bigger and bigger. But on the other side, the original bioprocessor, the human brain. It's doing all these incredibly complex things using only about 20 watts of power. It's that mind-boggling efficiency that has a lot of people thinking that biology isn't just something to study anymore. It might just be the next frontier in computing itself. Okay, so before we can even dream of computing with biology, we have to learn to speak its language first. And that, right there, is where AI is making its most immediate and, honestly, its most profound impact today, decoding our health on a level we've just never seen before. A really huge breakthrough in this area comes from an AI model called V2P, which stands for Variant to Phenotype. Now, this represents a massive shift. See, for years, we've been able to read the letters of our genetic code, right? But V2P is designed to figure out what those letters actually do, to predict the real-world health consequences of one specific genetic mutation. This is a game changer for getting to true precision medicine. What's really cool is that modern medical AI isn't just looking at one piece of the puzzle anymore. It's becoming multimodal. What does that mean? Well, it means it can process and connect the dots between completely different kinds of data, all at the same time. We're talking medical images, a doctor's text notes, your genomic data, and even audio from patient interviews. By pulling all that together, it can spot patterns that would be basically impossible for a human doctor to ever find. And here's an amazing real-world example of that in action: the liquid biopsy. These new AI language models can actually analyze the tiny, tiny fragments of RNA and DNA that tumors shed into our bloodstream. What's the result? Well, it means we can potentially detect diseases like cancer way, way earlier than ever before. We're literally moving from just treating a disease to actually intercepting it before it gets bad. So we've established AI as an incredible tool for analyzing data, but what happens when it stops being just a tool? I mean, what happens when the AI starts running the scientific process all on its own? This is where we're seeing the rise of the autonomous or agentic AI. These are systems designed to set their own goals and then figure out how to achieve them with very little help from us. And here's the wild part. These new systems can run the entire scientific research loop. An agentic AI can read all the existing research, come up with a totally new hypothesis, design the perfect experiment to test it, analyze all the data that comes back, and then, get this, refine its own idea and start the whole cycle over again. This is already being used to massively speed up research in things like drug discovery. And look, this isn't some far-off science fiction concept. It's happening right now. As this quote from Nature Communications points out, machine learning is already a huge influence in fields like biocatalysis, which is all about using enzymes to create new medicines. The AI is becoming a real, genuine partner in the lab. Okay, all of this has been building to what is, without a doubt, the most mind-bending frontier of all. We've talked about AI understanding biology and AI accelerating biological research. Now, we're going to talk about using biology as the computer. So welcome to the field of organoid intelligence, or OI. The whole concept is just fascinating. Scientists are growing these little 3D clusters of human brain cells, called organoids, in a lab. Then they connect these living neural networks to computers, and they use AI to send and receive signals. They are, in effect, creating a hybrid biological and electronic computer. I mean, the work being done here is just profound. By sending feedback to these organoids, like rewarding certain patterns of neurons firing, researchers are literally teaching these little mini-brains how to perform tasks. In one famous experiment, a brain organoid actually learned how to play a simple version of the video game Pong. It's incredible. Okay, So why on earth would we do this? What's the goal? Well, organoid intelligence has some unbelievable potential applications. We could create much more accurate models of diseases like Alzheimer's to test new drugs. We could better understand developmental disorders like autism. And by studying how these biological networks learn, we might even discover brand new ways to build better, smarter, and way more efficient artificial intelligence. Of course, when you're talking about technologies this powerful, they don't come without some really profound questions. As we start to merge AI and biology like this, we're stepping into a brand new ethical landscape, one we're going to have to navigate very, very carefully. This brings us to what's known as the black box problem. As these AI models get more and more complex, their decision-making process can become, well, a mystery, even to the people who built them. So let's say an AI recommends a specific medical treatment, but it can't explain its logic in a way a human doctor can actually understand and double-check. Should we act on that recommendation? How do we make sure someone is held accountable? And believe me, this isn't just a theoretical debate for philosophers. Governments are already trying to figure this out. This slide actually shows specific high-risk uses of AI in healthcare that were identified in a White House memo. We're talking about things like deciding on medical treatments, assessing health risks for insurance, and even deciding who gets care in a hospital. Making sure these systems are safe, fair, and transparent is one of the biggest challenges of our time. So from decoding our DNA to actually building computers out of our own cells, AI is giving us this unprecedented power to read, write, and even engineer the language of life itself. The potential to cure diseases and expand what we know is just immense. But as we get better and better at asking biology these fundamental questions, we also have to be prepared for the answers we might find. Thanks for watching.